Hi everybody, welcome back to Kosmos. I want to share how I calibrate my Witschi or Witschi, to pronounce it in the German way, watch timing machine. This is the Watch Expert, so I don't think they make this model anymore, but it was pretty ubiquitous throughout the 1990s and 2000s until Witschi came up with a much more sophisticated and kind of upgraded range. And in fact, the current entry-level model, I think, has a color LCD display and a few more functions. But this is a very sophisticated machine, and you do kind of get what you pay for. It was beautifully made, as I'll show you shortly. I had cause to believe that the machine had gone out of calibration, and for one reason or another, it was put out of service. I was pointed in the direction of a very interesting workaround by a friend of mine, and I'll get into that as the video progresses. Just a few words about how the system works, because that will help us understand the setup here. So this is a machine that is used to display the behavior of a watch, kind of take a short-term snapshot of how it's performing. So really the ultimate test of a watch's performance is to actually have it in use. What this does is takes a snapshot, a minute or two or 5 or 10 minutes of its performance, and gives you an idea of the likely behavior. Now fundamentally there is a microphone, and I believe that there's a little amplifier built into here, which then feeds into the back of this machine. The machine then compares the sound of the ticking of the mechanical watch to a high precision quartz crystal. So there's a time base built into this machine, and it is a thermocompensated quartz crystal, and by comparing the two, it displays a graphical output that indicates, whether the watch is gaining or losing, fundamentally. There are other very useful bits of information, analytical information, that are also displayed. I won't go into them much, but the point is, by comparing the sound of the ticking, it will tell you whether the watch is gaining or losing. So if we just I'll put a watch on this microphone, and so that this microphone is articulated, so you can move it into different positions. And so the idea is that you could test the watch in any one of the theoretically 6 positions in which it could find itself: dial up, dial down, pendant up. And so pendant is an old-fashioned word for the crown, because in a pocket watch the little loop around the winding button was where you attached a chain, and that was pendant. So pendant up, pendant down, pendant left, pendant right. These days it's more useful to refer to those as, say, 9 high. So in other words, if the 9 of the watch was in the high position, the 3 of the watch was in the high position, the 12 or the 6. So that would represent all 4 primary vertical positions of the watch. But in any event, you can see while I've been speaking, a trace has started to appear on this LCD, and there is a reading here of the rate in seconds per day. So currently it says gain of 1 second per day, but it's moving a bit. So as it goes through, it might say 1 second or then 0 again, just as a very, very subtle changes in the behavior of the ticking. The beat error, which is the difference, say, between a tick and a tock, are they identical or are they biased in one direction or another? The amplitude, that indicates how much the watch is worn, how much the watch is wound. This line, this solid line along here that keeps moving every 2 seconds, is the averaging. So it takes that chunk of the graph and gives you an average, and that's what that reading is. That's the measuring time there. So if we change the measuring time, but now it's straddling the edges of the screen, so it won't be that easy to see, but I'll change the measuring time by moving it down to 4 seconds, 2 seconds. So now there's only a 2-second measuring time, so that represents 2 seconds worth of ticking sounds of the watch. We can increase it to 4 seconds, and I'll wait an extra 4 before it shows another average. You can take it up to 20 seconds. I like to leave it on 10. Now, within this machine is a very sophisticated microprocessor, as you will see shortly. And in fact, the sounds, and if I just put the loudspeaker on, the sound of the ticking of a watch, so that's a normal watch amplified. The sound of the ticking sounds to the human ear like one pulse per tick. But in fact, it's made up of 3 distinct pulses, and they're separated by milliseconds. And that's because the watch escapement works in a very specific way, and there are three distinct events that happen when a watch ticks. Different clearances being taken up, and different elements of the escapement being struck or moved. And each of those events makes its own little sound. They happen very quickly, and so they merge into one to the human ear. But it's no trouble at all for a computer to kind of do a bit of spectrum analysis on that waveform and come up with the exact wave pattern. And I believe that this machine is programmed to listen for those 3 sounds, and unless it gets a very clear feed of the exact sound that a lever escapement ought to be making, it doesn't give you an output, which is a bit frustrating because it's very good, but for some purposes it's kind of almost too clever. And there are some watches, some antique watches or some watches that are never going to be in great condition, that a machine like this will simply refuse to give you an output because it's not happy with what it's hearing. So even though you can hear a ticking sound, and that ticking sound may in fact represent reasonable timekeeping, you will not get a trace out of a machine like this. There used to be an old-fashioned machine which used paper tape. So there was like a till roll, if anyone is old enough to remember what a till roll is. Just an ordinary paper ribbon, and there would have been either an ink cartridge that ran across the ribbon, or in very early machines a little spark, and the spark would burn the paper as the paper kind of fed through the machine. And whenever a single tick was heard, it would instigate the spark being struck, or the little dot being printed using ink ribbon, like a typewriter. And that was pretty foolproof, because if there was a tick, it would make a sound. Now, one of the reasons why this machine doesn't behave like that is so that it can cut out spurious noises, because even drumming your fingers on the table or whatever can upset one of the old-fashioned machines, because it's hearing all of those spurious sounds that have nothing to do with the watch behavior. So, in an attempt to make the machine foolproof, we also cut out its ability to test a bunch of watches that don't exactly conform to the theoretical high standard of Swiss watchmaking that this is designed to analyze and test. And that plays into the problems I've had in calibrating it. And the reason for that is I have a very high precision reference pulse in the form of this GPS receiver. So this is a little puck receiver, it's called, like a hockey puck, and it can pick up, the GPS satellite constellation and receive signals from them. Now, GPS satellites are very, very high. They have very high precision clocks on board, atomic clocks, which are accurate to a second in a million or more years, and that's what this is picking up. And using some not very sophisticated electronics, we can get a 1 pulse per second output out of this this little box. I will not use this for the purpose of this video, but I will do a follow-up video about getting a high precision 1 pulse per second from the GPS. It's not difficult. But what I have got, and I will show here, is an app. So there are a number of metronome apps available on the App Store, and also signal generators and function generators. Now this one is called Signal Gen, and I think, yes, it's called Signal Generator by Cat Eater LLC. Now you have to be careful if you do decide to follow these instructions, or to kind of get a 1 pulse per second app for your device. Be very careful, because very few seem to be able to go down to 1 hertz. Most of them seem to be kind of geared towards music, and then, you know, the kind of lowest frequency they want to display is, say, 440 hertz or some few hundred hertz number. And actually I had to download quite a few apps, and in fact I paid for at least 1 or 2, I think 2, which proved not to be very useful in the end, because I couldn't take them down to the frequency I wanted. So this one you can take down, so you can see you can choose the sensitivity of this dial. You can go in 0.1 hertz steps up to 100 steps. So I'll go down to 0, and then I'll click on the 1 and just take it up to 1, or you can also push it up or down by increments using those arrows. For some reason this doesn't output the audio to my iPad's loudspeakers, but it does output them to the earbuds, so I've got them connected to that. It actually works. I'd originally downloaded this for my iPhone, but as I'm using the iPhone for filming, you know, that precludes me showing it on screen. So we can get a nice pulse by choosing square wave, so you've got the different waveforms there. And if we play that, I'll just put this, so you can hear that that doesn't sound like, say, a pendulum clock or 1 tick per second, even though it's 1 hertz. Now the reason for that is, and this is a perennial cause of sometimes heated discussion among the theoretical horologists, and that is whether or not we should be measuring the behavior of watches and clocks in hertz, in a frequency measurement, in a frequency domain. And of course you've got a periodic oscillator like a pendulum swinging backwards and forwards, or a balance wheel ticking backwards and forwards in pure harmonic motion, and that would seem to be the perfect candidate for measuring in hertz, which is full cycles per second. However, as horologists, we're almost never interested in a whole full cycle per second. What we're interested in is the sound of the ticking of the watch, or the ticking of the clock. That is where our focus lies. And the ticking of pretty much every single watch made today, actually, oh yes, that is true. Pretty much every single watch made today, and most clocks, will have at least 2 ticking sounds for every full cycle of the oscillator, which means that hertz immediately becomes an awkward unit. What has traditionally been used is beats per hour. You see, even on there it says beats per hour. Now, just by dint of experience, we become conversant with different numbers of beats per hour. So we've got 18,000 is the traditional one, which is about 5 ticks per second. And that's ticks per second. However, in modern Swiss parlance, they wouldn't call it an 18,000 train, they call it a 2.5 hertz escapement, which doesn't really describe what the thing does. And I'm very much one for an kind of analog way of describing things. You know, you want your brain to get a grasp of what's happening in the real world based on the units of measure. So 1 hertz is not giving us the pulses we expect. However, we can't take it down lower. This app doesn't go down lower, and the minute you take it down any less than 1, it stops ticking. So if we take it back up to 1, we can cheat. It's gone back to sine wave. Just put it back to square wave. Ah, it stopped working all of a sudden. There we go. We can cheat by using this sawtooth waveform, because in fact it's counting every little vertex as a pulse. So 1, 2, 3, 4. But you can see that if that's 1 and the next one is directly below it, in fact 2 are overlaid over each other. So effectively half the frequency by using that. Actually, I've just realized that I've had this ticking probably very volubly during my rambling, so my apologies if that's been annoying. Now, one would have thought, and this is what I did using this app. I just put the little earbud on this sensitive microphone, and I think there's a little amp inside this unit. And I'll just hit the loudspeaker, and in fact there you can see the little LED blinking every time it receives a pulse. So that means the thing is working as expected. It's sending a beautiful crisp waveform into this machine. However, it's not picking up. If I change the setting here to automatic, which is the one you'd normally have it set to when you just put a watch on the microphone, it doesn't even begin to register. The LED pulses, okay, but nothing even attempts to come up on screen. If we change the setting there to frequency, which is what I had it on a minute ago, it does in fact come up with the correct frequency, 3600 beats per hour, which is 60 pulses per second. But occasionally you'll see this word appear in the top left hand, amplitude. So again, what this machine is hoping for is a nice, stable input of the type of waveform it wants, which is that 3 peaks spaced very close together, and then it knows it's listening to a watch and not somebody drumming on the table. And so it simply will not pick up. Now, there is this device. I'll just silence that for a second. There is this device which is called the Expert Q by Witschi, and it's sold as an extra, or was sold as an extra, in order to test quartz watches. And there are 2 DIN sockets there with the same configuration. One is mic in, where you'd plug this in and it would kind of pass it through, so you never needed to kind of keep swapping cables, and the output, which then goes into the back of the main machine. So we could pass the mechanical signal through this into there, and if we had that set to mechanical, it would simply just loop the signal straight into machine. It's when we click this over to the quartz settings that more magic happens. Now, this device, as I said, was sold as an extra, is full of circuitry and predominantly op amps and differential amplifiers, which I'm guessing kind of gives a very crisp pulse, which is then fed into here. But I also believe that it must send some message to the mothership that it's to expect this crisp pulse, and I haven't been able to decipher what that code is in order to override this machine's expectations. But if we look at, and so that's why I'm not using this, but it turns out, because I was a bit depressed at one stage, because I thought, oh, that would be really disappointing if in order to calibrate the machine you have got to go through the Expert Q, because in fact I was using my iPhone with a signal generator, and when I put the loudspeaker over this sensing area here in this black leatherette patch, in some positions I could get a signal, and I could get a trace on the main screen. And I expect that's because it was detecting the electromagnetic pulse that was coming out of my iPhone speaker rather than the audio pulse, because this doesn't have a microphone built into it. It does have two very high impedance sensing coils. So it's got quartz analog, and so that's feeling for the magnetic pulse of the stepper motor in a quartz analog watch, analog spelt in the American way. Quartz LCD. Now, I'm not sure about that. I expect that it turns it into a more sensitive measuring device, but I expect that it also has additional filters, because in an LCD there's more going on in a kind of liquid crystal display quartz watch. Quartz current, I'm not so sure either, because there's no real way to sense this unless this, I don't have the manual for this, so I don't know what quartz current is listening for. And then tuning fork. So again, tuning fork, you've got coils that really output sine wave at 300 hertz or 720 hertz for most typical tuning fork watches. So I presume that it's just changing. This is just changing the sensitivity and the gain, perhaps, of the built-in amplifiers, so that the output is always at the same level. Because for tuning fork you might need much stronger gain than, for example, a quartz analog watch, which has a pretty chunky electromagnetic field. And so, as I say, I was thinking, well, I'm a bit defeated if I have got to use this to input my 1 pulse per second. I mean, I don't want to take anything away from Witschi, because they're a good company, and I really do support anything that's kind of homegrown, made in Europe, good sound, proper engineering. But it is interesting to know about, and I'm sure there are watchmakers and other people interested who may never really find themselves in a position to send off for their machines to be calibrated, or you may live on the other side of the world. It may be prohibitively expensive for you to even send the thing. So as I say, I don't want to do them out of business, but there must be people who will benefit by this information who would never have employed the calibration services of Witschi in the first place. So I hope, on balance of things, I'm being fair in revealing how I am able to work around the quite sophisticated technology that they have built in here. So as I say, with that in mind, I was a bit depressed thinking that you might need this magic box of tricks in order to get the signal readable by the main box. However, as it happens, that is not required. And I'll go into that exactly how in just a moment, but I should say that I was chatting to my friend Jim Arnfield, and it was really him who came up with the idea, and he's so practical and has got such a fantastic lateral thinking, problem-solving brain, that when he suggested this, I thought that was absolutely genius. And the reason I'd asked him is because I know he's calibrated his own machine, also using the 1 pulse per second GPS signal, but he used this box because he had one anyway. And I don't have this box, in spite of what appearances may suggest. This doesn't belong to me. I borrowed that from a friend, just to try and do this investigation. So, all credit to Jim Arnfield for the idea of how to do this. So, what we've got to do is deceive the machine into thinking that it's picking up a proper watch pulse. So, it obviously doesn't do that. I'll just put the ticker back on. It will not pick up or start displaying this because it thinks that it hasn't got the right waveform on a kind of micro level, and it's right. It doesn't. It's not getting what it is being taught, or what it was taught to ask for. So we have to fool it, and the way we do that is we input our audio signal exactly as I'm showing you here, and you may need a few attempts at this because you've got to kind of time it right. Just get a normal watch and also put it on the microphone there. Now, the audio from this will overwhelm the 1 second per 1 second pulse, and you'll see that immediately the machine is happy. It starts picking up the signal from the watch. So you'll see what I'm doing here is I've got the crown pressed against one of these metal probes, which is integral part of the microphone. So the machine's very happy. It's picking up the signal it expects. Now, with as little noise and interference as possible, I'm going to draw the watch away. And yes, I was lucky I got it first time. Sometimes, if you pull it away at just the wrong moment, the machine loses interest. Maybe because there's too much of a gap between the next tick and it just stops listening. But if you time it just right, I would say halfway between the seconds, it'll carry on listening and it picks up those 1 seconds. And you'll see there's a little bit of noise. Sometimes that noise carries on for 10 seconds or more before the machine works out that it's now listening to a different frequency. In fact, I'll just start it over. So you can overwhelm the machine by banging it like that, and that just kind of shuts the amplifier down because it's got gain control. So just have a look at this number here. So that's telling us the frequency, the true frequency of the watch, which is 28,796 beats per hour against the theoretical 28.8. That's 4 beats per hour out. So watch that number as I pull this away. Now, the machine is confused. It still thinks it's listening for this number, but it's still picking up the pulses. Suddenly, now it's detected that it's got a 3,600 pulse, and it's corrected it and start outputting it as a straight line again. As I say, sometimes this kind of scatter graph or scattering of dots appears for quite a wide area on the screen. Now, we can tell immediately that the machine is out of calibration because of this pronounced rise in the graph. This is in fact, a very high precision output, more than accurate enough for the purposes of regulating a watch. And so that is unacceptable. It's saying 4 seconds a day. I'll just increase the measuring time. It is 10 seconds, so that's okay. So I'll just make it 20 seconds, but I don't want to labour the point. But you can see immediately that the machine's out of calibration because this is a 1 pulse per second, and I'll reveal to you that I was playing with this earlier and I forced it into such a state of miscalibration for the purposes of clear illustration. It was in fact very, very close before. It was cycling between just about 0 and 1 second over a very long period. So that's how I can assure you that the received pulse is accurate, quite aside from the fact that it is being used or being output by a very high precision computer. You know, if you think about the processor that drives that iPad and the number of crystals and resonators that serve as various time bases. Now, we have to open up the machine and adjust the trimmer capacitor that is expressly for the purpose of calibration. Now, while I do that, I will put this kind of garish piece of foam down on the bench. And I'll just stop it for now. I'll switch it off. And a few words about the disassembly of these machines if you choose to do it yourself, because there are a few pitfalls. So you'll see that this kind of leather look theme is in force. I don't know, there's a kind of instrumentation back panel, typical instrumentation back panel of the 80s, although this machine was from the 1990s. Oh, there it says year 2002, but I think this was made in the 1990s. This is not the first of these machines I've opened, and I can tell you that the little standoffs that these screws go into are very, very fragile, and I have broken most of the ones I've opened. Maybe that's because I'm ham-fisted, maybe and I do believe that it's a combination of that and the fact that this type of plastic, whatever it is, I don't know if it's some kind of ABS or something, may be prone to aging or some kind of stress. And once I open it, you'll see I haven't done up the screws very tightly, so you've got some machine screws here, so they go into little brass inserts which then peg into the molded plastic standoffs. You'll see that the printer output is blanked off with this little panel. So you can connect a little line printer to some of these machines, which will give you a permanent record. And in fact, before I turn that around, you can just see where it says print. There's a print button there, and it will just print like a snapshot of what's on the screen. Now, bear in mind that that's protruding off the surface, so we want to kind of be careful. So this is just a back panel that can be lifted away with no trouble. These rubber little feet will catch, so slide it away that way. Oh, and the ubiquitous kind of electronic carbon that is attracted to these things is present there. And in fact, there was a lot more of that kind of thing inside the device. But as I say, I've had this open before, and I've cleaned it out. So I'll just pull off these little feet. Maybe I won't need to. I didn't do it before. Now, the idea is to try and pull this board out absolutely square and not tilt it in any way, because that's part of the problem. And you can't push from the front because this screen is glued onto the plastic body, and that's not part of the circuit board, so the screen isn't removable, and if you try and press it, you'll just break it out. So we have to try and lift this away, or maybe drop it out, and that's what I did the last time. So just very carefully drop it out, and I'll just put it on his face now. You can see that I've epoxied some of these little standoff. So that one broke, that one broke, that one broke more recently. Those two are intact. And what you've got are these little brass studs. And I believe that they were actually pressed into the board, because the board has evidence of the kind of splines having cut into the edges. So I think that those studs were probably originally pressed into that board to locate them, rather than being kept behind in the body or the shell. So we'll come back to that later. So what do we have here? Just a quick overview first. So there's the front of the machine with the little push buttons that control the functions. There's a little LED that comes on when you press freeze. That's a little pulsing LED. I'll give this a light wipe later. Now, just a quick overview actually, because it's very interesting to see the way something like this is made. And it is absolutely beautifully made, and exactly what you'd expect from a Swiss company like this. This microchip here, the Z84C000, is a microprocessor. It's an 8-bit microprocessor made by Zilog. So that's a powerful computer, given the expectations of what this, of what's expected of this tool. You've then got I think that's a memory chip. Oh no, I think that's eight bytes of memory there. There is also an I/O controller, which I think is this chip here, which controls all the input and output behavior. And this is an interesting. And that's a proprietary. Must be some kind of proprietary chip because it's signed Witschi. And there's another W Expert with a little sticker with the numbers 99 on it, which made me think that it was made in 99. And I think that may be a programmable chip, like an EEPROM. And this, I wouldn't have expected Witschi made this chip, but they would have had it made exclusively for them. So a powerful computer right there. This is interesting. This LT1039CN16 is a driver for a printer. So whether or not the chips have been programmed to output a printer, but it's kind of cheaper to make the board consistently the same and maybe just change the programming. I've not tried to connect a printer to this little socket, so I will try that later, but I've never tried. This is the interesting part here. So this is a little polystyrene box, like a little cooler box or an esky, and underneath there will be the quartz crystal that is the heart of this machine's timing, and it's against the oscillations of this crystal divided by I think this chip is timing and interrupts, and so you'll end up with 1 pulse per second, or well, actually you'll end up with much less than 1 pulse per second, but there'll be CMOS division circuitry among this that will get the quartz crystal's output down to kind of human levels. Actually, I wonder if we can see what frequency that crystal is. I don't want to force it off. And then over here, you've got all the audio. I expect these are audio amplifiers, maybe. That's an op amp, TLC274CN. That's an op amp, or 4 op amps, presumably to sharpen up the input pulses, maybe. So there's the board. This is the little capacitor or the trimmer that we use to adjust the frequency. So that is going to be the target of our work today. So I'm going to reassemble this kind of naked, and what I'm going to do is it's not really necessary, but I'll just keep that vaguely in contact. Oh, and the power. So I'm going to just rest this on the cables, which isn't the best practice, but it's only for a few minutes. Like that. And then I'm going to plug my audio on again. I'll plug that in, switch it on. And we're going to switch this on. So the manufacturers say about halfway is the kind of ideal gain. Automatic gain control will sort out the rest. Right, iPad's been switched off. So you've got our pulsing LED. Nothing on the display. So we'll change the value of this automatic to frequency. And then get our cover watch to fool the machine. So there you can see the kind of scattered field was slightly wider than the last time, but still it pulled itself into good behavior pretty quick. Now I'm going to try and reach behind. I'm going to use this rubber-coated screwdriver. I don't have kind of electronics screwdrivers, and I'll touch only the plastic parts for whatever it's worth. Now, what we're aiming for is a perfectly horizontal line. And I'm afraid this isn't going to be. So now I'm turning this, say, about a quarter turn clockwise when viewed from the screwdriver's side. So it seems to have tightened things up a bit, because now it's saying 2 seconds a day, whereas before it was about between 3 and 4. I'm going to change the measuring time. Actually, if anybody does have the original manual to this, I would appreciate maybe getting in touch. Because I'm intrigued by what this means on the right. I think on the front panel it says param, or like parameter, and I have no idea what that does. And also the SEL, the select option on the left here, I do really wonder what that means and what it's capable of doing. So if you do have a manual, it'd be great to hear from you. Okay, so the other thing I should have said is that it's important that the crystal is allowed to stabilize, and it takes some minutes, maybe 10 minutes or so, I think, for the temperature to stabilize. And so this kind of thing ought to really be done after the machine has been on for some time. So the machine had been on for some time when I started filming, and so that's why I don't mind, me switching it off for a couple of minutes while I disassemble the box. I don't believe that'll have a material effect on the calibration. Anybody from Witschi watching this will probably be tearing their hair out as I speak. My apologies to your barber. Okay, so I'm going to go a bit more in the same direction. Well, it was maybe about 1/10 of a turn. Seems to be moving in the right direction. So just while we're sitting watching this for a second, it may not be intuitive as to why this will gain or lose if the machine's out of calibration. And so if you think about it, say we're giving the machine, say the machine was, say, losing a lot, so, you know, under par. It would therefore see a perfect timekeeper as gaining, if you see what I mean. So a perfect timepiece would have a relative gain compared to a device that was losing by comparison. And that's exactly what we're seeing here. So in other words, before calibration now, the oscillator was losing seconds per day. Which made my iPad look like it was gaining against it. It's about another tenth or so. The cap isn't marked in any way, it's just kind of suck it and see in terms of how much you turn the capacitor. It's one full turn. Like it makes no difference if you turn it more than one full turn, because there's only like one full turn available, and if you keep turning then you just go around and start from the beginning again. So in other words, we can't go we can never get too far out. Like it's a bit idiot proof in that sense, because there's a limited amount that you can force it out of calibration, but conversely a limited amount you can pull it back into calibration. That doesn't seem to be changing. What I will do is just change the graph resolution, which is this number, so that goes up to 5. I mean, it's just a relative number, which just scales up gives us more vertical resolution in the display. So I'm back after about 4 minutes, and as you can see, that graph is like a mill pond. It is absolutely flat without the merest hint of a ripple or a slant anywhere. So I'm happy with that. I'll keep an eye on this, and also once I've finished rigging up my GPS receiver, I'll retest this and I'll report back. I've also taken the opportunity while this was ticking away to just do a last bit of cleaning. Now, actually, my iPad may die any minute because it was on 10% about 10 minutes ago. So we don't really need this to be running anymore. So I'll just stop that. I'll just reassemble the device here, and I'll just add a few more comments about the housekeeping and also, oh, that wasn't screwed in, it was just held in. Just to reiterate the superb quality of this tool. I have no idea how it compares to the inside of, say, one of the Chinese Timegrapher machines, but certainly, you know, it's got an 8-bit computer. It is beautifully made in Europe, and I would encourage those who can to kind of buy the premium product, because I believe it'll serve you well, and you're supporting a local industry. I mean, there's something to be said for buying cheap, crummy things, or things that don't matter, just really cheap as possible. But globalization has its price, and so I think that there is a good argument for supporting not just buying electronics from Asia at every possible opportunity, if you can help it. I've cleaned up this cover a bit more. There was a lot of dust inside the. You see, there's kind of blobs of hot melt glue that hold this piece of acrylic, and there was lots of dust in there where it had, dropped in there over the years. So I just blew that out with my compressor from the front, and I also just pressed these little brass inserts nicely home. And it also gave them the opportunity to crack out if they wanted to crack out, because the last thing you want to do is assemble this and then find a piece of plastic floating around after you've reassembled it, like a piece of busted plastic. So that didn't crack out, which is good. So we'll reassemble this. I'll just give this a last wipe. I'd lightly clean that with a little microfiber cloth, and I'll do the same again. Oh, I've noticed just a tiny bit of that black carburizing or soot that gathers, I think, electrostatically. On plastic surfaces like this, sides of PCs and that. Anyway, so that's that. And we'll reassemble this carefully. And as ever, even with a watch, no matter how clean it is, there's always guaranteed to be a glaring big piece of dust after you've reassembled it. I'll try and somehow earth this, so I'll just touch. I've got an earthed piece of metal here. Just try and earth that, because a lot of these plastic components will attract dust due to static electricity, and if you earth it, the tendency is less. Try not to use that capacitor as a handle. And just get that round the little feet and drop it on as squarely as we can. Right, that's it. And I'm not going to rest it down there because, as I say, the control knob protrudes. So I'll just hold it up with one hand. I also took the few minutes to give that more of a wipe, and that's kind of staining. That is really clean now. So I'll reassemble that panel. And the one to watch out for is this little earth strap here in the corner. I'll put that one in first. Just hold it in place like that. I won't do up these screws ridiculously tightly because the little inserts are kind of split. And I think that as you do up the screws, they expand ever so slightly, almost like a wall plug. And I think that may contribute to the further degradation of the little plastic posts that they live in. So I'll just do it up tightly enough. It's these bottom three that are cracked. Just do it up enough to bite. I also cleaned off, there were a couple of stickers there. I cleaned that off. And I used, just as a way of an aside, by way of an aside, this stuff, which I bought in Canada when I was visiting there. I think you can buy similar things around the world, and it's an orange peel solvent, and the main constituent is D-limonene, which I read about, and it's distilled, like steam distilled from orange peels, especially like in the orange juice industry. So they squeeze millions of oranges, and then what do they do with the peels? Well, one of the things they do is make a cleaner, and it's an incredible solvent because it tackles things sometimes that white spirit or alcohol and other solvents don't touch. And one of the things I found it's very good on is a type of glue used on paper labels and sticky surfaces. And actually another thing that, quite surprising, a very good solvent for that type of thing, but I don't know if it still applies, like in the 1980s and 90s, there's types of solvent and propellant available in household products were quite different, before climate change and that became so troublesome. But what was it, like toilet air spray, air freshener in a can. The propellant in that, not the propellant, but just the liquid, always seems to have the ability to loosen stickers much better than a lot of other solvents, like lighter fluid or whatever. So try those two tips sometime and see if it works for you. And so that's my timing machine back together again, back in perfect calibration. I didn't have to spend 300 francs, but I believe I spent a lot more than 300 francs just investigating. And all credit to Jim Arnfield for having the inspired idea of deceiving the machine by holding a watch up to it while the seconds pulse was also coming in. And so, yet again, the old school trumps us young upstarts when it comes to creative ideas and experience. Counts for a lot. So thanks for watching, it'd be great to hear if any of you have had experience calibrating your own timing machines and what trials and tribulations you've had and how you overcame them. So thanks for watching, and see you again sometime.